So in this video, we start looking at bases in Banach spaces. In Hilbert spaces, we have orthonormal bases, and they are very useful in doing analysis in infinite-dimensional Hilbert spaces. They allow, for instance, generalization of the concept of diagonalizing a matrix in linear algebra through the spectral theorem. Now, in Banach spaces, we do not have a notion of orthonormal basis simply because we do not have a notion of orthogonality in general. Now, what we do have, nonetheless, is the idea of a basis, that is, the idea of being able to decompose uniquely a vector into a linear combination of basis vector. Now, we want to do that not just in an algebraic sense, but we want whatever sums we get to converge in the norm topology of our Banach space. So that leads to this particular definition of a basis as due to Schauder, so we often refer to this definition as the definition of being a Schauder basis. But I'm going to drop the name Schauder and just call it a basis in the Banach space. This is the appropriate notion for what we're doing that respects both the algebraic and the topological structure of Banach spaces. So we say that the sequence En is a basis if any vector in our Banach space can be decomposed as a linear combination of the basis vectors in a unique way. So there's a unique sequence of coefficients such that we have this decomposition, and whenever I write this equality with an infinite sum on the right, I am implicitly saying that the infinite sum converges for the norm of my Banach space. Now, associated with that notion, I have two natural objects. I have the functionals that corresponds to projecting into the direction defined by the basis vector E capital N. So this is a linear map that takes your vector, and any vector can be written in that way, and returns the coefficient in front of E to the capital N. Now we'll see that this defines an element of X star in the next proposition. Now, related to that, we have the family of partial sum projections operator. So you can take a vector X, which a priori is given by an infinite sum of basis vector, and you can truncate that infinite sums up to capital N here. Right, and this is a projection onto the first capital N plus 1 element of the basis. Right, so this is a simple enough idea, but in order for this idea to be useful, we are going to have to show various properties of these En stars and these Pn, and ways of checking whether or not a given sequence is indeed a basis. So let's have a look at the next proposition. So the proposition 10.2 says the following. Now you can form a set of sequences by looking at all the families of coefficients An such that the sum of An, En converge, right? So these are really the sets of all the coefficients, all the sequences of coefficients that corresponds to a vector X in our Banach space capital X. Now, if you put a norm on that set of sequence S, and the norm is defined as the supremum of the norm in X of this finite sum, we will see first that in doing that we put a Banach space structure onto S. And once we have a Banach space structure onto S, we'll find that actually the map that maps the coefficients in S to the corresponding infinite sum in X, which has to converge by definition of S, this will define an isomorphism between S and X. So whenever we have a basis, we can really isomorphically look at the space X as a space of sequences over R, just looking at properties of the coefficients, right? If it were a orthonormal basis in a Hilbert space, really we would have an isomorphism between the Hilbert space and little L2, so we could look at the norm of a vector in the Hilbert space through the little L2 norm of its coefficient. Now this is not going to be that simple in a Banach space to actually realize what sort of norm S is. Nevertheless, there is an abstract isomorphism between a space of sequence and the Banach space whenever the Banach space has a Schauder basis. Now, this functionals here that we use to project onto the direction of En, well, they will be element in the dual. We'll prove that in 3. And they are very much uniformly bounded, so in the sense that let's just imagine that all of your ENs have been normalized to have norm 1, then the EN star will have to be uniformly bounded. Now, we did not assume as part of our definition of a basis that the ENs have norm 1, like we would in an orthonormal basis. But one thing for sure is that if you multiply the norm of En by the norm of En star, these quantities stay uniformly bounded. That's part 4 of the proposition. Now, we don't have a concept of orthogonality because we cannot identify the Banach space with its dual. But as always, we recover some idea of orthogonality by looking not just at the Banach space, but at the pair formed by the Banach space with its dual. And in that sense, the En star combined with the En, this double family, one in X star, one in X, forms what's called a bi-orthogonal family, in the sense that En star applied to Em is going to be 0 whenever N is not M, and is going to be 1 whenever N is equal to M. So this here is really the replacement in general Banach spaces for orthogonality of a basis, for an orthonormal basis in a Hilbert space, where really the functionals En star would be identified with the basis vectors themselves. And last but not least, these partial sum projections here would have to be uniformly bounded. So part of being a basis means that the sequence of partial sum converges and in fact is uniformly bounded. Okay, let us prove proposition 10.2. Now the first thing we have to prove is that the space S is a Banach space. Now proving that we have a norm and that this forms a vector space is easy, so I'm just going to show that S is complete for the norm that we've defined. So let's pick a Cauchy sequence in S, and I have to construct a limit for that. So what does that mean that the sequence is Cauchy? It means that for every epsilon there exists a capital J in N, such that for all little j greater than capital J, greater than K, say greater than capital J, and for every capital N in N, by definition of the norm of S, the sum from, let's call it N, equals 0 to capital N of An J minus An K, En has to be smaller than epsilon. Let's call that 1. So this is the assumption that I have a Cauchy sequence in S. Now, having that, if I apply it for capital N equals 0, then I get that A0J minus A0K is smaller than, well, multiplied by norm of E naught is smaller than epsilon. So, okay. So that tells me that this, in particular, this tells me that the sequence A0J indexed by J is Cauchy. And then you can go to the next one, A1J minus A1K, and this would have to be smaller than 2 epsilon divided by norm of E1, right? Because you rewrite it as A1J minus A1K times E1 plus the sum up to 0, which we've bounded, which is also bounded by 1. Okay, now you can do that inductively, and you get that ANK minus ANJ in absolute value is always smaller than n plus 1 times epsilon divided by the norm of En. That's for every n in N. Right, just applying the condition 1 again and again, and really using the fact that it's uniform in capital N. Okay, so, and that's, for all j greater than k greater than j, for every epsilon there exists a j. Right, so that's what we get from the condition 1. So now I can define a Bn to be the limit of the A and J as j goes to infinity. Of course, I've got for every n, a and j as a sequence indexed by j is a Cauchy sequence in R, and R is complete. So this is well defined for all n in N. And now what I want to show is that this sequence Bn is actually in S. But what have I got? Again, from 1, I have that for every epsilon, there exists a j in N, such that for all j greater than capital J, well, the sum n equals 0 to n, and that's for every capital N, let's take the sup in capital N, of the sum of a n j minus bn times en is smaller than epsilon. So I'm taking the limit as k goes to infinity in 1. Now, okay, having that, I get that for every epsilon, there exists a capital J, such that for every n and m in N, and let's say n being greater than m, I have that the sum from n equal capital M to capital N of Bn En is smaller than the sum from n equal capital M to n of Bn minus An capital J times En plus the sum by triangle inequality m to n of Anj En. Right. But the first part of the sum, right, is the sum up to capital N minus the sum up to capital M minus 1, say, is certainly smaller than 2 epsilon by property 1, by the fact that I have a Cauchy sequence, or more precisely by 1 prime that we've deduced here. And then I have this other bit here, which for a fixed capital J certainly goes to 0 as capital M and capital N goes to infinity, or more precisely this series with a and capital J coefficient is convergent, therefore the partial sums form a Cauchy sequence. So what we have is that sum n equals 0 to capital N of Bn En as a sequence indexed by n is Cauchy in X, hence convergent. Okay, but what does that mean that this converges in X? That exactly means that Bn is in S. Right, so we've proven 1. We've proven that S is complete for its norm. The norm that we define is clearly a norm. It's a vector space, so S is a Banach space. What we got to do next is show that this Banach space is actually isomorphic to X. Okay, so let's have a look at the map T from S to X that sends a sequence An to the sum An En in the Banach space X. Now we know this sum converges by definition of S, so this map is well defined, and it is a bijection because En is a basis, since En is a basis, right? So En being a basis, the uniqueness of the coefficient An means that if T of An is equal to T of Bn, then An has to be equal to Bn for all n, so that gives the injectivity of the map, and every element in X can be decomposed in that way. That gives the surjectivity of the map. Okay, now do we have an isomorphism? Well, let's have a look at continuity. So what happens when I look at T of An? Okay, and look at the norm of that in X. Well, that is the norm of the sum An En, n equals 0 to infinity, which is the limit as capital N goes to infinity of this sum. Well, actually, it's certainly smaller than the supremum capital N in N of the sum of the An En. Right, for n large enough, this is going to be this infinite, the norm of the infinite sum, it's going to be smaller than 1 plus epsilon for any epsilon times this quantity. Okay, and this quantity, well, is precisely the norm of An in S. So we have an isometry. Now we have an isometry, it's a bijection, and therefore T minus 1 has to be bounded from X to X. That's a consequence of the open mapping theorem that we've seen before. So T is an isomorphism. And as proves 2. So we have an isomorphism between the space of sequence S and the Banach space X. Now let's have a look at the next item. We need to show that the coordinate functionals en star really are functionals in the sense they're elements in x star. Now for that, let's define the map for every n phi n. So let's look at it through S. So let's look at the map from S to R that sends a sequence, a j, to just the nth element of that sequence. Okay, now what is en star of x? By definition, it is phi n of t minus 1 of x, right? You take your decomposition of x, t minus 1 gives you the sequence of coefficients, and phi n returns the coefficient an. That's for every n in n and for every x in your Banach space. Okay, so in order to show that en star is bounded, because t is an isomorphism, we really just need to get a bound on the phi n's. But what have I got for the phi n's? If I look at phi n of a sequence aj, for any sequence aj in S, okay, this is an, and an is, well, certainly equal to 1 upon norm of en times an en, and then this has to be equal to, I forgot to say that I take my en to all be non-zero. I mean, if not, if you had one en that were to be 0, you could not have uniqueness of the decomposition. You could put whatever coefficients you want in front of that en. So this is a consequence of the definition. So this is 1 upon en times the sum j equals 0 to n of aj ej minus the sum j equals 0 to n minus 1 of aj ej. Okay, let's not take our n to be 0. For the zeros component, it's even easier. You just write it as a0, ae0 here. All right, and say this is certainly smaller by triangle inequality that 2 divided by norm of en times the norm of the sequence aj in the sequence space S. All right, and what does that tell us about en star of x? For every n in n and for every x in x, this tells us that this is smaller than 2 divided by norm of en divided by, well, multiplied by the norm of aj in S, which is the norm of t minus 1 of x in S, which is smaller than 2, divided by norm of en, multiplied by norm of t minus 1 as a bounded linear map from the Banach space x into S times the norm of x in the Banach space x. And that is exactly saying that en star is in x star. Of course, it's also linear. Okay, so that proves 3. What about 4? Well, 4 is really a consequence of what we just done, because when I look at en star times en, we've just seen that the norm of en star is smaller than 2 divided by the norm of en times the norm of t minus 1 as a bounded linear map from x to S. And so you multiply that by the norm of en and you get 2 times the norm of t minus 1. Okay, and that's finite, and that is independent of n. And so this proves 4. Cool. What about 5? What about this analog of orthogonality? Well, if I take an n and an m in n, and I look at en star applied to em, well, I can rewrite that as en star applied to the sum of delta jm ej, right? Well, I'm using the Kronecker symbol. Delta jm is 0 for all values of j's except when j is equal to m. Okay, but then by definition of en star, knowing that's what I'm getting here, is just delta n m. So that proves 5. Very good. What about 6? The very last one. Now you take an x in x, and you take an n in capital N, and you look at Pn of x. Now, Pn of x is what? Well, it is equal to, so if I take the supremum over all n, that's better. If I take the supremum over all n, then I get literally the norm of t minus 1 of x in S. That's the way the norm in S was defined. So this is certainly smaller than the norm of t minus 1 times the norm of x as a bounded linear map from x to S. Sure, but that means that for every x, this supremum is bounded. So now I can use the uniform boundedness principle, and I get that the supremum of the norm of the Pn as bounded linear map on x, not just pointwise for every x, has to be finite. And that proves 6. Concluding the proof of proposition 10.2. So these are reasonably easy facts to prove, but they will be very handy in dealing with basis. Okay, so now we will prove another little proposition that characterizes the fact that a sequence is a basis. So there's 3 properties that characterize being a basis. One is that all of the vectors En have to be non-zero. That's kind of obvious. If you have 0, then you could multiply it by whatever you want and it wouldn't change the sum. So you would lose uniqueness of the decomposition if you didn't have that. You have the fact that the span is dense. That's also kind of obvious. This is telling you that you can approximate any element by limits of finite linear combinations of the En, which of course you want to be able to decompose any elements in the basis. But the really non-trivial fact is fact 3, and fact 3 is telling you that if you project down to the first n element and you project further down to the first m elements, then the norm of Pm of x will be controlled by a constant independent of n and m times the norm of Pn of x. So these 3 properties put together actually imply that En is a basis. So you have to check a density argument. Of course, you have to make sure that you are not adding 0 to the basis. And then really the key things to prove is to prove some uniform boundedness of the projection onto what you think is the basis. So let's prove this proposition. Okay, so one direction is easy. If you have a basis, then it has to satisfy 1, 2, and 3, and I'm going to leave that as an exercise. I kind of said verbally a minute ago what you have to do to prove that. So I'm going to do the other direction. I'm going to assume 1, 2, and 3, and I need to deduce that En is a basis. So the first thing we'll do is we'll define a set E to be the set of all vectors for which there exists an En, not necessarily unique at this stage, for which x can be written as the sum of the an En. Right. Now, one thing for sure is that the closure of E has to be x, and that's because of 2, right? The span is dense in x, and any finite linear combination of the En is going to be in E. So by taking limits of these things, you definitely guess any element in x. So what we really want to show now is that E is also closed. Then this would tell us that every element x has a decomposition. Then we'll still have to prove that it is unique. So let us prove that E is closed. Okay, so let's take a converging sequence in E. Let xj in E converge to some x in X, and I have to show that this X is actually in E. So what can I say about the xj? So the xj's, because they're in E, they're of the form sum of an j en for some anj's. And now if I take any n, I can look at anj minus ank for any, so for any n in n, for any jk in n, and I can say that this is 1 upon the norm of En. It cannot be 0 because that's property 1, so let's say that's by 1, times the sum from m equals 0 to n, let's do that for an n that is non-zero, of amj minus amk of en minus the sum m equals 0 to n minus 1 of the same thing. Okay, you gotta treat the case n equals 0 separately, but it's even simpler. So now when I look at this, it's the difference of two sums, one up to n, one up to n minus 1. And so by property 2, this is going to be smaller. Is that property 2? No, it's property 3. It's going to be smaller than 2c divided by en times the sum m equals 0 to capital M amj minus amk en, and that's going to be true for any m that is greater or equal to n. Okay, so what does that tell me? Now here what I've got is 2c en times the norm of xj minus xk. Right, so I can take a limit as capital M goes to infinity of that. Yeah, and that doesn't increase the norm. So, okay, so we have that for every n and every j and every k, and we know that xj as a sequence in x by j is Cauchy. So this proves that for every n in n star, you can do the n equals 0 case yourself separately, anj as a sequence indexed by j is Cauchy in R. Well, okay, therefore it converges. So we're going to define Bn equal the limit of the a and j's as j goes to infinity for all n in n. Now what we have to do is show that the Bn, or the sum of Bn an, is x, such that the limit of the xj x belongs to E. Now the way you do that is that you pick, you give yourself an epsilon, you pick j, such that xj minus x in norm is smaller than epsilon. And then, for every n in n, you look at sum of Bn en up to n minus x. And what can I say about this? Well, I can say that this is smaller than xj minus x for the j I've chosen, plus the sum of Bn en minus the sum of a and j en up to n, plus, by triangle inequality, plus the rest of the sum that describe the xj. So the sum from capital N plus 1 to infinity of a and j en. Right, but that second sum here, so this is smaller than xj minus x, which we already know is smaller than epsilon. Picked my j in that way. And then the second sum I've got here is a sum n equals 0 to n. It's a limit, let's say, as k goes to infinity, of the sum of the a and k en minus the sum of the a and j en, because for all n between 0 and capital N, Bn is the limit of the a and k. So this converges to what I want. Okay, and then I have plus that rest here. Now, the point is, because I have property 3, I can say that this is smaller than epsilon plus the limit as k goes to infinity of c times, xk minus xj, and then plus the rest again. Right. Sure, but passing to the limit, this is smaller than epsilon plus c times x minus xj, so I get 1 plus c times epsilon for the j I have chosen. Okay. And notice that that j was chosen just dependent on epsilon. It's independent of n. So what we have now is that for every epsilon, there exists a j in n, such that for every n in n, sum of Bn En, n equals 0 to capital N minus x is smaller than 1 plus c epsilon plus the rest of that convergent series. Alright, so now you just have to pick your n large enough. So for every epsilon, there exists a j in n, and there exists a n bar in n, such that for all capital N greater than n bar, sum of n equals 0 to capital N Bn En minus x is smaller than 2 plus c epsilon, say, by making this smaller than epsilon for capital N large enough, depending on j. Right, that is to say that the sum n equals 0 to infinity of Bn En exists and is equal to x, and so x belongs to E. Therefore, E is closed, and that is to say E is equal to x. So for all x in X, there exists an An in a sequence of real numbers such that x can be written as the sum of An En. And now all we have to do to finish the proof that En is a basis is show that this decomposition is actually unique. So let's do that now. Okay, so how do we prove our uniqueness? Well, we assume that we have another one. That there exists a Bn, another decomposition, such that x is equal to Bn En. Okay, so now for every capital N in N, I can say that the sum from n equals 0 to capital N of An minus Bn En, I want to say that this is 0. Well, what I know is that by property 3, it has to be smaller than a constant times the full sum all the way to infinity. But its full sum is 0, right? Because sum of An En converges to x and sum of Bn En converges to x. So we have that these sums are 0 for all n, and therefore the sum from n equals 0 to capital N minus the sum from n equals 0 to capital N minus 1, say, so therefore An minus Bn times En is 0 for every n. And that is only possible if An is equal to Bn, because the Ens are never 0. So by property 1. And that concludes the proof of this proposition. Really, to be a basis, you need the closure of your span to be the whole space. You need all the vectors to be non-zero, and crucially, you need uniform boundedness of the partial sum projections. That is property 3 in this proposition.